Swayam Prabha. Digital India. Educated India.
We are going to now start understanding what we mean by convergence of a sequence of random variable, right. So we already known, like when you have a given sequence, what it converges to, and the limits are very important, because many of the times like integral differential functions are all defined in terms of the limits. And also when I have a process, let us say I have modeled it as some stochastic process which are indexed by time, I want to understand how this process evolves over time, right. So I would be interested in knowing, as I let my t go to infinity, how my process evolves and behaves. Suppose you are investing your money in a gamble, every day you are going to win or lose, and based on that, every day you have some money left with you, and you want to understand eventually, if I continue to play the same game, eventually as the number of plays becomes large, will I end up with a positive amount with me, or it will all go to 0, or it becomes negative. So you want to understand, as time evolves, or in my stochastic processes, as the index becomes large, how my process looks like. Okay, is there any limiting behavior in that? But then the question is, fine, we understand what we mean by convergence of a sequence of random variable, convergence of a sequence of numbers. Then what does we mean by convergence for random variables, right? So we need to make that notion of convergence of a sequence of random variables precise, and that is what we will focus on maybe in the next 2 to 3 classes. So let us say I have a sequence of random numbers, random variables, all random variables defined on the same omega sigma. So another thing is, I am going to only focus on our random processes here, or a sequence of random variables which are indexed by discrete, numbers. So here n is 1, 2, 3, 4 like that. Okay. Now the first notion of convergence in almost sure sense. Okay, we are going to say the sequence of random numbers xn, they converge almost surely if probability of limit as tends to infinity of this x is going to take the value x. So what I mean by this limit here, I have already said that limit of xn is equals to x, right. So what I mean by this here, suppose you fix omega belongs to omega, and then you are going to look at xn of omega. Is this a deterministic sequence, xn of omega? Yes, right. If I fix an omega, this is because xn is a function of from capital omega to r, right. So if you fix an omega, this is some real number, and I have a sequence of such real numbers, and I know what I mean by convergence of this sequence of real numbers, right. That is a standard convergence, and whatever is the limit. Now what we are saying is, if the meaning of this is if limit of xn of omega so this is the short form for this. I am going to look at omega and see whether this sequence of xn omegas converge to my limiting random variable, and then look if wherever that convergence happens I am going to look at all these omegas and then look at whether that probability is equals to 1. If this happens, then I am going to call my xn converges to x almost surely. So let us look at an example. So let us say I am going to define a sequence of random variables like this. Okay, so before that I want to introduce this notion of unit interval probabilities. So earlier we have already defined the notion of what is a event space, what is sigma algebra, and what we mean by probability space and all, right. So now I want to define a special probability space which is as following. Let omega is as that omega is, so omega is basically interval, and then in this outcome omega is drawn from omega with preference, no preference towards any subset. Okay, in a way like I am saying that I am going to draw omega from this sample space in a way uniformly, right, without giving any preference to any of this subset. Then I am going to now start constructing my event space on this. Let us say F to include all intervals. What I mean by this, I am going to say that I am going to take so these are all possible intervals, right. Take A and B, and which is A is between 0 1 and also B is between 0 1. This is going to define one interval, and let us all possible intervals be contained in this event space. Okay. Now that I have been drawing omega from this capital omega without any preference to any of this subset, then one natural way I am going to assign probabilities to this intervals is B by A. Okay, assume that B is going to be greater than or equals to A. Now I have defined omega, I have defined my F partially here because I only said it includes closed, this intervals here, but if it has to be a sigma algebra, then I know that it has to satisfy the properties of sigma algebra, which says that complements should be there and their unions, finitely many and countably many unions should all be there, right. So if intervals are there, then the open sets are also there in the sigma algebra F, right. I will have open intervals in this, I will have closed intervals in this. By taking their unions, I will have sets which are open at one end and closed at other end, and I will have all such kind of combinations if I have to look at a sigma F. Now when I have such a sigma, then to make this completely probability space, I also need to say how I am going to define probability for each of the elements in my F, right. For intervals it is easy, I have defined like that. But if I am going to look at all possible elements that are in F, how I am going to define it. So
one particular element also we have defined, because probability of A will be A minus A, which is B.
yeah, if you are going to say B equals to A, then you have only one element and for which you are saying 0. I am saying you take any interval here for which you have defined like this, and you can go like this, and if you want this F to be sigma algebra, it will have all possible subsets of my 0 1 interval, right. So the worst case what you can take, we can take this F to be a power set of this, that means it includes all subsets of the interval 0 1. But here is some technicality here. When we do this, it so happens that we will end up with certain sets for which we will not be able to consistently assign probabilities. I mean that comes from some complicated analysis or some better understanding of the real sets, but we will not go into that. But what we are going to take is when this F2 include, what we are going to take this is F to be the smallest sigma algebra containing all subintervals of omega. So we take F to be the smallest sigma algebra. So you can come up with many sigma algebra which will contain all these intervals, right. But we were going to take that sigma algebra to make this to define this, which is the one which contains all subintervals of omega. Okay, is this point clear? So we are going to take all. So the way we are defining F is, let it include all the intervals. To make it sigma algebra, we also has to allow it to possibly include all open sets, their unions, their intersections, so many combinations are there. So you may end up with so many sigma algebras, which so many F's which may on its own satisfy the properties of sigma algebra, but among all them we will take the one to include the smallest one which includes all the subintervals. Okay, so this is just to make this bit more formal, and then when we have such an F which contains all the smallest all these subintervals, we know how to assign probability to them, and using that we can try to define the probability for each of the element in that F. and such probability space we are going to call it as unit interval probability. So for our all practical purpose, what we mean by unit interval probability space is my sample space is unit interval and my sigma algebra is such that it contains all possible intervals, and on each of the intervals there I am going to assign probability like this if I have an interval. So we only need to take, so our understanding of unit probability space will be just this, okay. So but it has something more to it in terms of how this f is defined in terms of the smallest sigma algebra containing all the subintervals. Okay, fine, this was just a detour, and this is what our understanding of unit interval probability space. Now to understand our notion of convergence, we will be looking at examples or random variables defined on this unit interval probability space, because this is going to be easier for us to understand. So I am going to take, let omega fp be what I call as unit interval probability space, okay. Now I am going to define my random variables like this, fix an n, and that n is going to be such that for any omega that is coming from capital omega, it is going to be defined like this. Okay, now let us try to map this. So let us say this is x1 and this is my omega. So how does x1 look like? It is going to be a linear curve, right? It is going to be linear and going hitting at 1. And how does x2 look like? It is like a quadratic, right? It goes to 1 here. And how does x3 look like? So its curvature will open up this side or that side? It is going to be right like this. Now let us try to apply this definition here and see where it will converge. So okay, before this, as we saw that as we move from 1 to 3, the curvature is opening towards the right, and you as n goes to infinity, how does this curve look like? Right. So it is going to almost 0 till this point, and at omega equals to 1 it is going to be 1. So in this case, in a way, as n is tending to infinity, we see that this sequence of graphs here are converging to a place where it is all 0 and then it suddenly shoots up to 1 at omega equals to 1. So let us take that to be our limiting x. So then let us try to analyze whether this property holds, and in this case can we call xn converges to that x. Okay, so claim is we want to check whether xn converges to x in almost surely where x is at omega equals to 1. This is my x. So now can we verify and see whether this guy satisfies this property, whether this is true or wrong? Yeah. So let us take a omega which is not at, so let us take omega which is not 0, not 1. Okay, if you take any omega not 1, that means it is strictly less than 1, what is going to happen? Xn of omega will converge to what? It is going to converge to 0, right? And x is also 0 in that range. And if you take omega equals to 1, what is this going? Guys are going to converge. Xn of omega, they are going to be 1, and what is this guy is? This is going to be 1, right? And then it looks like so all omega which are between 0 1 are going to satisfy this property, so they are included in this set, right? And what is the probability of that set? What is the probability of that set? 1, right? Because every point in omega has satisfied this, and so probability of big omega is 1, that we already know. So by this definition we already know that this example converges to x, which is like this, almost surely. Just let me check this at the point omega equals to 1. At omega equals to 1, these guys are all 1 1 1, and okay. So fine, if I have defined my x equals to like this, which is 1 only at omega equals to 1. So let us say I am going to define my x to be in a slightly different fashion. I am going to take my x to be 0 all the way, even at omega equals to 1. It is not jumping at all here. Is it true that in this case, let me call this as x prime here. Is it true that my xn converges to x prime almost surely? Why? Yeah, but I don't care about 1 points, right? What I care about this probability. So as you said, other than omega equals to 1, everywhere this holds. Only omega equals to 1 not included. So what is the probability of this set where all omegas are included except omega equals to 1? It is going to be still 1, right? Because probability of that singleton 1 is going to be 0. Is it true that in that case my xn converges to x prime also here? Because that singleton values did not have any mass in our example here. Okay, so both are valid, like I can say that both converge to this random variables. Okay, so that's fine. Another thing we will right away notice is when we have a deterministic sequence of random variables, whether my limit was always unique. Was it? Like, is it possible to, let's say I have a deterministic sequence an, can it have two limits? So then limit is always unique, right? But when we are talking about convergence of this random variable, that's not the case, right? So here x is the, when I said xn converges to x, this is my limiting random variable and these are my sequence of random variables. So it's fine, that's not the case that I have only one unique random variable. So but as you will see that this is only at the points which carry 0 mass. So in that way this random variable and this random variable on this probability space, they are identical because they only differ at points which have 0 mass. Okay.